All right, 5.3 is the start of, or introducing, what's called the fundamental theorem of calculus, which involves a very special type of integration that solves applications. It's a big theorem. It's sort of the big second fundamental idea that calculus was created to solve. The first big fundamental idea is what we spent most of the semester on, which was instantaneous rate of change, right? My derivative, my speed of my function, my acceleration, and so on. And so in chapter 5 here, we're doing antiderivatives. Well, antiderivatives have another big concept that they're used, which is called integral calculus. All right, integral calculus is used to find the area under the curves. And what it really is, it's an accumulation. All right, integral calculus studies the accumulation of a function's values as its input values increase. That's what we're going to eventually get to. You will have to bear with this first part of 5.3. We're going to get to this, what's called the fundamental theorem of calculus, this accumulation function. But in order to get there, all right, there's some theorem we kind of have to get through. The understanding the underlying concept of that fundamental theorem of calculus, all right? Just like when we had the derivative, there was the fundamental understanding that the limit of the average rate of change found my instantaneous rate of change. There was no direct way to find instant rate of change, right? We had to use average rate of change. Well, something similar to that is going to happen here. So like I said, this first section is the setup and the foundation to understanding integral calculus and getting to that big theorem called the fundamental theorem of calculus. Now, we are going to keep it fairly basic in this class. We're not going to dive too deep into the theorem. We're going to keep it, like I said, on the basic. If you wanted to do a more in-depth, that would be the other calc class. All right, to sort of set up where the problem came from, right? We make observations. In science and mathematics, they make a lot of observations. Same thing was done with the derivative. They observed velocity exists at any moment in time. How do I find that velocity at any moment in time? Well, it was a harder question to answer, right, than it seems it should be. Well, the same thing here. We're going to observe areas, but as it turns out, finding the areas isn't as simple as it would seem to be. All right, so do a simple example. Again, remember, this all relates to derivatives, rates of change. All right, so assume that we have oil consumption in a given region. All right, we know that oil consumed over a 4-year period was constant. All right, we know that it was constant at 1.2, meaning every year the rate of consumption was 1.2 million barrels of oil per year. And so that's a rate, all right? It's a derivative, a rate of change. All right, it's just a constant rate of change, meaning every year that's the rate at which the oil was consumed. It was constant. Well, to find the total consumption then, so rate of change would be the speed at which consumption is, so it'd be kind of in terms of velocity, it would be how fast you're traveling in your car. Well, I want to know how much distance did I cover. Well, same idea here. This is how fast the oil was being consumed. I want to know, well, how much oil was consumed in total. All right, and so what we do is, well, if it's consistent, it's not too hard when it's a consistent case. The region consumed a total of 4.8 million barrels of oil over the 4-year period. And the way we find that is we take the rate of consumption times the time elapsed. And the units kind of tell us that's what's happening, right? 1.2 is the million barrels of oil, so I'm going to do MBO for my million barrels of oil per year consumed times the 4 years, right, where they're consuming that at that given rate. And so my year rate cancel out, leave me 4 times my 1.2, which leaves me with 4.8 million barrels. I don't know why I did B for barrels of oil. Alright, so again, that would be the million barrel of oil. Alright, now I'm going to relate it to the graph. Alright, so relating this to the graph and area, because that's what this is really going to boil down to. Alright, so if I draw my oil consumption as a graph, alright, so this would be my time in years. This would be the rates of consumption, millions of barrels per year, barrels of oil per year. Alright, so time starts at 0. We're going out 4 years. Alright, 1, 2, 3, 4. the rate at which we were consuming was constant at 1.2 million barrels of oil per year, meaning it was constant over those 4 years. That's F of t, which is my horizontal line, 1.2. All right, 4 years is when it was, so again, this would be the rate, 1.2 million barrels per year. This would be the time, 4 years. And if I look at this area of this rectangle is 4.8, right? If I take the area of the rectangle, its base is 4, right? That's 4 units, right? So this distance here on its base is 4 units. Its height is our 1.2, and so the area would be base times height, which would be 4 times our 4.2, or 1.2, which comes out 4.8. And so the area, this area here, is equal to the amount of consumption, the area under my rate of change function, which I can find this area because it's a nice rectangular curve. All right, so the area under the rate of change is equal to the total, the accumulation of all the barrels of oil that were used up. Total barrels consumed. You can read that. From 0 to 4, right, over the 4-year period. If I went 0 to 10, same thing, I just take 10 times my rate of change, and I get the total number, the barrels consumed over a 10-year period. Where it gets tricky, so in this case it's easy to find area, and hopefully it's easy to understand that this area, which again is my rate of consumption times the total time elapsed, right, gives me my total number of units used up. In a nice simple case like this where my rate of change is constant, it's the same, I can find it because my area comes out to a nice rectangular shape. Well, in most cases rates of change aren't necessarily constant. Right? For an example, suppose that a different region over that 4-year period has a rate of consumption that varies over those years, meaning they don't necessarily consume the same amount of oil every year. All right, suppose that rate of consumption is modeled by this function, which is not a constant function, right? It's a cubic over the 4-year period. All right, so again, F of t is the rate of consumption of millions of barrels per year over the 4 years. All right, the area that we need to find, all right, this is still time in years. This is still my rate in millions of barrels of oil per year. Right, if I plug 0 in, it starts out at 5. All right, and if you graph this on the calculator, it goes up slightly, then back down, and then it starts to kind of take off. All right, and that's kind of where it is after 4 years. All right, so this would be the 4-year picture of my F of t, all right, which again is the rate at which oil is being consumed. So it starts off going up, and then there's a little dip in it, and then it starts to take off. It starts to grow really fast. They're consuming more and more and more oil as it moves closer and closer to that 4. And what we have to find, well, this area still represents the total amount of oil that was consumed. So that area is still the total amount of oil consumed over the 4 years. Alright, so over the 4-year period, we want to find the area under the curve. Alright, well this time it's not a nice, neat rectangular shape. Alright, this time it's a shape that's sort of varying with my function, right? This is my rate of change function, my derivative, over this time period. But I can see that it exists. I know they're consuming oil, they're consuming it at different rates over the years because it's changing as it's moving over the years. All right, well, how do I find that area? And that's the question that was answered, or that's the question that was asked way back when during Leibniz and Isaac Newton's time. All right, we can visualize it. We see that there's an area. We know they consume so much oil over the 4-year period. How do we find that area? All right, and again, it's kind of like the velocity problem. We know it exists. How do we find it? All right, well, it's not an easy question again. It's not one that's necessarily easy. There's a lot that's underlying in it. And so again, this is sort of the setup to understanding, well, how to find that area. All right, so I'm going to do another graph just to kind of compare it to stuff we're going to be looking at, which will be, change in cost, change in revenue, change in profit. So suppose I have the derivative of the cost function. All right, so this is a derivative. All right, it's the rate of change of cost in dollars per calculator. All right, so X represents my calculators. This would be my derivative of my cost in dollars per calculator. All right, per calculator produced. Suppose that we want to find the area under my derivative from 0 to b. So 0 would be there, b would be somewhere, into my curve, so that would be my b value, right? That would be where we're ending, and I want to find this area. All right, that would be the area I'm trying to solve for. All right, I want to find that area. Well, how can I find it? Well, as of right now, we can't. There's no direct way to find it. All right, we can't yet. That's what we're going to kind of go through and discover the theory behind, well, how do we find that? And then there will be a process using integration and antiderivatives that will allow us to find that area. At the very least, though, you should be able to determine, well, why would we want to find the area, right? What is the area telling me? All right, well, the area giving me, so this is the cost in dollars per calculator produced, right? So B would represent the number of calculators produced. And so if I find the area under the derivative of the cost from 0 to b, if you can read that, from 0 to b, that will tell me the total cost. That will find the total cost in dollars to make B calculators. All right, that's what that area is. If I find this area, this would give me out total cost. And cost is not consistent, right? At the beginning it costs a bit, but then it starts to decrease in cost a little bit, and we go down, and then cost goes up again, and then cost comes down. At least the rate of change of cost, right? It's going down, up, and then back down. All right, if I find all of this area, that would tell me my total cost, right? That would give me the cost value. And I know it exists, right? If I have a rate of change of cost, I know I have a total cost. I'd find the area, that will give me my total cost for my calculators. Well, that's the question we want to answer, right? That's what we want to get to. All right, so the area problem, as the preceding examples, touches on the second fundamental problem in calculus. How do we calculate an accumulated area in a region bounded by a positive function, right? How do I find this accumulated area bounded by a positive function? Positive function, I mean it's graphed above the x-axis. Bounded by vertical lines. That's my starting point, my stopping point. So my vertical line would be 0, would be where I start. B would be where I stop, right? If I go up here, 0 is a vertical line where I start. B is a vertical line where I stop, right? And this is the area I want to find. All right, well, how do we find that? All right, how do we calculate that accumulated area of the region bounded by my function, the x-axis, and a starting line and a stopping line? All right, well, we're going to look at another example, and I'm actually going to pick that up in my next video. We're going to look at another example involving a market research type, all right, where we have lines and stuff, and I'm going to set that up in my next video and go from there. And so again, the next couple of videos are going to be sort of theory, but it's a big theory, big idea we're leading up to.